Okay, so the very first concept we learned about that was related to derivatives was the power rule. So I graphed different functions. So we started out first with a constant. And we would look at the slope function at prime of x, which is like so we would look at the slope. So at x, the slope m, let's look at negative 3. 1, 2, since there's no rise, then our slope was 0 at negative 2. Same thing, the slope there of the line is 0. And so on and so forth. So we found out for that the slope was always going to be 0. We did this for a linear function. We found out the slope was just the slope, right? Slope of run. So f prime of x equals 2. And then for a quadratic function, x squared, okay, our slopes became flatter and flatter as we approached 0 until it became 0 here, and steeper and steeper. And we found out there was a pattern, and it was a linear pattern as we changed our slope, and our slope was actually a linear function. We did the same thing for a cubic function. And we found out that our slope function was quadratic. So f prime of x was 3x squared. So we started noticing this pattern that when you have a function, a power function, so x to the n, then your slope function, this is your slope function right here, was n times x to the n minus 1. Okay, we would bring down the coefficient and then subtract, or not the coefficient, we would bring down the power and then subtract 1 from it. And that was our slope function. Some examples, okay, would be what's the derivative of, or what's the slope function for 3x cubed? Well, f prime of x, we bring this down, so 9x, and then we subtract 1, so 9x squared. Yeah. What if you get the more general polynomial? So general polynomial is in the form a coefficient times a shift to the right or left to the nth power and a shift up or down. So if you remember from pre-calc, this is a stretch or a shrink. This is a shift right or left. And this is a shift up or down. Okay. These are your transformations. So for a general polynomial like that, your derivative would be, you still bring down your coefficient, so you would n times a. You'd keep your x minus h in here. You would subtract 1 from your power. And since this is just a constant number and we know the derivative of a constant is 0, this would just go away. So there'd be, this is what you would be left with. Let's do a couple examples of that. So let's say, for example, you had something like f of x is equal to 3 times x minus 2 to the 4th plus 6. Your f prime of x, well, you'd bring down your 4, so it'd be 4 times 3, which is 12. and then you'd be left with x minus 2, and then you'd subtract 1 from the power, so it becomes 3. This becomes 0, so you're left with 12 times x minus 2 cubed. So you can practice this on your own. Maybe stop the video right here and practice. You can do, find the derivative of g of x is 6 times x plus 2 to the 4th. G of x is equal to 7 times x minus 3 to the 5th plus 8, and go from there. Okay? The other thing is when you have a sum of two functions, so let's say you have something like f of x plus g of x, the derivative is just the sum of the derivatives. Okay? So if you have a sum of functions, the derivative is just the sum of the derivative of each individual function. So for example, if you have something like x cubed plus 3 times x minus 2 squared minus 6x, you can see I have three different functions. I have x cubed, 3 times x minus 2 squared, and then minus 6x. So I just find the derivative of each. So the derivative of x cubed is 3x squared. The derivative of 3 times x minus 2 squared is 6 times x minus 2. And the derivative of minus 6x is minus 6. So there's my derivative function right here. So let's see, is there anything else about that? I mean, that's pretty much all we learned about the power rule. It's relatively useful just to learn it, memorize it, and practice it a lot. And then in the next video, we'll go over the actual derivative, the actual definition of the derivative itself, and how to use the definition of the derivative to then find derivatives of other functions.